Hi guys, in this lesson we will implement some basic codes in Python programming language in order to create the PDF decision or the probability density function decision or the probability density function classes in Python programming language. After that we create the Gaussian mixture model in order to build the class definition for the given data, for example the x1 and x2, and then we will continue with the navy bias classifier. Okay, so the first code we should give the posterior PDF decision.py in here. In order to build our code we need to give the numpy as mp import matplot lib.pyplot as plt from cgpy.stats import norm. Okay, first we need to create the generated synthetic data. We must assign to random seed body in here like this one in order to generate the random numbers, and after that we can build the x1 data with the mp random dot normal. Location means the mean value, scale is the standard deviation of our algorithm, and size is equal to 100. Okay, and so x2 dot for data should be created with the same analogy, but in this case this is the 180. Okay, so in the first place we have the size 100 and 100. We should assign the prior probabilities in here. Okay, prior x1, prior x2 0.5, because we have the equal size at the x1 and x2 with the number of the 100 data points. Okay, so in order to test our algorithm we need to give the heights or new heights. For example, we should discriminate to the short and tall person. Okay, and so we need to create this term 165, 175 and 185. Okay, and after that we should create the likelihood probabilities by using the norm function in here. Okay, likelihood x1 can be created with the the normalization.pdf. okay, and new heights location mp mean x1 data, and scale should be assigned with the mp std x1 data. Okay, this returns to the our probabilities for a given new height value for the location of the x1 dot, the mean values, and the x1 dot or data x1 data, the standard values. Okay, also we can create the likelihood x2 in here like this one. Okay, this is the one class and this is the another class. After that we should create the posterior probability in here. Posterior x1 can be calculated with the likelihood x1 times prior x1 divided by likelihood x1 times prior x1 plus likelihood x2 times prior x2. Okay, because in this nomination we have the two probabilities, but the whole probabilities or the whole classification contains the c1 and c2 class. Okay, for a given x1 and x2 likelihood, and so this the our ratio for the posterior probability x1 for a given the total probability, and after that we should calculate the posterior x2 with the x2 and x2. Okay, just simple as that. After that, we need to create the predictions, and so the predictions can be calculated with the argmax arguments. Okay, and so this selects to to each class for a given data. Okay, and so mp v stack should be created with the posterior x1 and posterior x2 in here, and axis equals 0 plus 1. Okay, this returns to 0 and 1 value, but we have two class 1 and 2 should be assigned by using these terms. Okay, and so the argument maximum can be selected with the posterior x1 and posterior x2. Okay, and so this returns to the which is the posterior probability is higher than the other one. Okay, and after that we can create the height prediction in zip new heights and predictions. Okay, and print f height with the height value, and also we should give the predicted class x prediction. Okay, and so in the output of this code we will reach to the 165 is possessed with the x1 and 175 and 85 is possessed with the predicted class x2. Okay, because we have the denomination, mean and standard deviation values, and then we have these times. Okay, and also we can plot the data nomination in here. PLT hist can be utilized in here. Histogram diagram means 20 alpha 0.5 and label class x1 and density is true. Okay, also we should give the x2 and x2. This is our total data. It's given in here, and PLT scatter should be built with the new height, because this is the new observation. Okay, and p0's creates the dimension of the given matrices in here with the values of the 0, and marker should be assigned x, color should be assigned red, and label should be assigned with the new heights. Okay, and PLT title can be built with the Bayesian Decision Classification. PLT x label is equal to the height. PLT y label is equal to the probability density. Okay, PLT legend and PLT show must be given in here. Okay, and so in this nomination we have the 3 data in here. For example, the 1 data possessed with the class 1 and 2 data possessed with the class 2 data. Okay, this is just simple, but we can model anything by using these terms. Okay, in the second example we should build the posterior PDF classes structure. Okay, firstly we should get this same structure in here, like this one, but with some difference, because the observation or measurement from the system should be built with the MP linspace 255, 150, 200 and 100 data. Okay, and so we have the 100 data to be tested in this system. Okay, and also likelihood probability is also same with the previous one, Also every code is same with the previous one, and so I can copy up the whole of the things in here, and after that we can build the plot history in here. Plot data plt hist x1 data bins 20 alpha 0.5 label class x1 and density is true. Okay, also we should give the x2. Okay, it's the histogram plot. And after that we should give the plt scatter function by using the new heights mp0s like new heights. In the new heights we have the 100 data at this moment. Okay, and marker x, colors red, and label new height. So plt plot also be given new heights for a given posterior probabilities x1 and label posterior prop x1 and color is assigned with the blue and x2 is the green. Okay, after that we can copy of the whole of these things. And so if I rerun this code with multiple data in here, and then we have this kind of Bayesian decision classification in here, like this one. This red x values is the new height, but the R classification performance is coming in here like this one. And so this is the distinction point of these terms, because if you have this point and then at the left hand side of these terms we have the posterior probability x1 or the class 1 data, but at the right hand side of this diagram and then we will have the posterior probability x2 diagram. And so this probability can be reached by using these terms, and so we can classify everything that we know the proper mean and standard deviation values of these terms. Okay, so in the third example we need to talk about the Gaussian mixture model. Okay, week 12 3 posterior GMM class. Okay, as always we do, we should generate these values with the same with the previous one. Okay, and after that we should fit the GMM in here. GMM x1 Gaussian mixture model should be utilized in here, but in this case should from learn mixture import Gaussian mixture. Okay, Gaussian mixture can be utilized with the 4 components and random state 24 in here, and GMM x1 fit can be used to fit the whole data. Okay, reshape -1 and 1. This is the combination of the proper size of the data generation in here. Okay, just simple as that. And also we should give the GMM x2 values in here, like this one for the x2. Okay, we have 2 model, but we model these terms using the multiple mean and multiple standard deviation values in order to improve the R performance to detect any class in here, which is in this case we have 2 classes, short and tall. Okay, So how can we calculate the likelihood probabilities using GMM? Luckily we have some basic tools in here, like this one, MPX GMM X1 score samples, which is the codes of the what for a given new height values, reshape -1 and 1, okay, and also we can create the what the X2, okay. These are codes to what to build the R nominations. And so these are the R likelihood, and then this GMM X1 is what is derived from the Gaussian mixture model, and so GMM X1 also possesses the method for the what the log likelihood of each sample automatically, okay. And so if we provide the new heights values, this score sample, and then this returns to the what the likelihood values of the X1 and X2, okay. So the rest of the code with the same with these nominations, okay, because we just have the likelihood, and then we can create the what the posterior probabilities in here, like this one, likelihood prior X1 and prior X2 can be assigned in here, okay. I'm sorry, X1 and X2, okay. And so if I rerun this code, and then we will have the same diagram, but this is the simple case. But what happened if I choose the component number of the 12 and 12 at the both sides of this code? And so we will have the more strict line in here, because we have increased the number of parameters related to mean and standard deviation values, which means that we can reach the boundary conditions by using the higher component number, because we can model it, or we can split the every data into the specific mean and standard deviation values, and then we can observe these terms like this one, okay. This is the strict line to increase the R performance, okay. But if I choose another component, GMM X2 is given 2, and then we will have some anomaly conditions in here, like this one, because the X2 cannot be easily created, or cannot be modeled everything in here, because we don't have enough components in here. But in X1 we will reach the highest values performance in here, and so we have the notch points at the plot values on these terms, okay. So you need to optimize the R code or your code in the next case, and then you can model everything that we have in these terms, okay. So what happened if I create the 12 posterior 2D GMM classification with the 4 values? And so this is a more complex case, but this is a useful case to propose or show the advantage of usage of the Gaussian mixture model instead of the probability density function, okay. Now numpy smp import matplotlib pyplot splt from scikit-learn mixture port Gaussian mixture model from matplotlib.colors import listed color map, in order to assign each class to a specific color map. Okay, this is just the simple, or these two components, just demonstration of your codes. Okay, and so firstly generate the synthetic 2D data in here. MP random seed 42, mean x1 is equalized to MP array. We have the vector in here instead of one scalar values, 160 and 65. Okay, these are the two mean values for a given 2D vector. Okay, and so x1 covariance matrix can be created with what, the MP array. And so we have two dimension in here, 25 0 and 0 10. Okay, and also x1 data should be generated with what, the MP random multivariate normal mean x1 and x1 with the size of the 100s. Okay, just simple, or the same analogy can be created with what, the x2 data. Okay, but in this case 180 and 7 is the 30 and 50. Okay, so we can assign the new observation in here like this one. In your application you have the two-dimensional data. You don't need to use the create the what, the synthetic 2D data. Instead of using these terms, you must calculate the mean and covariance values of the 2D data coming from the measurements or the something else in your mechatronic application, and then you can build the what, this nomination. But the new observation is the new measurements in here. Okay, MP random uniform, the low value is the random values 155, and the high values can be created 190, 70, and size of these terms must be equal to the what, the 102. Okay, 100 row and 2 columns for a given what, the x1 and x2 data. Okay, these are the random numbers. Okay, in order to show the performance of these components in the Gaussian mixture model, we should give the what, the component numbers via list 2 to 6. Okay, we will test to what, the 2 components, 3 components, 4 components, 5 components, and the 6 components in here. Okay, and so we need to create the num subplots in here like this one, len component numbers. Okay, we generate the what, this kind of subplots in here, and plt figure fig size is equal to the what, 16 5 times num subplot. Okay, and so after that we should create the for loop in here for I num components in enumerate component numbers and 1. Okay, and so we get the index and the number of components for a given what, the enumeration of the component numbers 2 to 6. Okay, so firstly at each case you must feed the GMMs like this one. GMM x1 can be assigned with the Gaussian mixture model, and components should be assigned with the different components number, and random state is equal to 11 for example, and GMM1 x1 is fitted with the x1 data. Okay, and also we should give the what, the x2 values in here like this one, but this can be assigned to the what, 33. Okay, after that at each case we should obtain the prior probabilities. Prior x1 is equal to the len x1 data for a given what, the total number of data, x1 data plus x2 data. Okay, also we should give the what, the x2 prior. Okay, after that we should get the likelihoods of each data. Likelihood x1 can be assigned with the what, the joint probabilities of these terms, GMM x1, score samples, right, with a new observation. Okay, and also we should create the what, the GMM x2, score samples. Okay, these are the codes for the what, R nomination to get the joint probability or the likelihood of this model. Okay, after that we can calculate the what, the posterior probabilities in here using Bayes theorem. For example, the posterior x1 is equal to what, the likelihood x1 times prior x1 divided by two terms, which is given in the what, the total nomination is this. Okay, these are the what, the total calculation of the posteriors for a given data. Just remember that the likelihood x1 times prior x1 plus likelihood x2 times prior x2 equals to the what, the px, or the presence of the 2D dimensional data. We can reach easily by using these terms. Okay, and x2 can be calculated also in here. And after that we should give the decision making in here, predictions, MP arc max value, but we need to create the V-stack formulation in here, posterior x1, posterior x2. Okay, so axis equals 0 plus 1. This is the class number. Okay, and so we can decide the whole the components by using these predictions with in terms of the what, the this nomination. Okay, so plotting the data and class posteriors probabilities, incorrect meanings. For example, we should create the what, the mesh grid application in here, because if we have two-dimensional data, we should give the x mean and x max value from the what, the MP mean function in terms of the what, the MPV stack values. Okay, and V stack returns to the what, the R nominations in terms of the what, this one, x1 data, first column. Okay, and x2 data, first column. Okay, these are the range, and so we can create the MP max values by using these terms. MP V stack, we combine the whole denominations, x1 data, right, 0, and these terms also given with the what, no, it's the tuple values. This is like, is that it's the same. Okay, and after that we can assign the MP DAX. Okay, these are nominations, and also we should create the what, the Y values in here, and the column 1, column 1, column 1, and column 1. Okay, so these are the general plotting data, but we should get the total mean and max values from the observation data or the training data. Something else, okay? And so after that we should create the MP mesh grid in order to build the 2D dimensional model. MP lin space x mean values, x max values, and 100, okay? And MP lin space y mean values, y max values, and 100, okay? And so the grid can be built with the these terms: MP C XX variable and YY variable, okay? This is just combination of the 2 data in order to build the R total representation, because that X1 finally can be calculated with the GMM X1 score samples grid value. This is the new observations just now, and after that Z X1 equals to the Z X1 reshape with the XX shape, okay? And also we should build the X2 values in here, like this one, and X2 and X2, okay? So in order to build the demonstration of this code, listed color map can be used, okay? And so we have the specific code FFAAAA and sharp AAAAFF. This is the reverse order of these terms. After that we should create the subplots in here, num subplots. It's the total number of the subplots. It's given in here, okay? 3 and I minus 1 times 3 plus 1, okay? This is just a simple subplot creation at each forum, okay? After that we should create the contour 1 using the PLT contour with the XX, YY, Z X1, alpha is equal to 1, line whites is equal to 2, and colors black, okay? And also we should define the system contour 2, but with the posterior probability of the 2, okay? And after that we should create the PLT scatter diagram for the training data in here. X1 data is 1, and label class X1, and alpha is the opacity rate of the R applications, and X2 can be given in here like this one, X2, and after that PLT title F posterior probability into the space, okay? And we should also give the number of components, because each components have different performance. Num components, okay? And so PLT X label is height, PLT Y label is, for example, white, okay? PLT legend, and after that PLT C label is equalized to the contour 1 inline true, and font size should be given also in here 8, and color is black, okay? For the contour 2 should be given in here, okay? This is the first case for the for that's only creating the training data, okay? And after that we should give the what our observation. I know this long, but in real application, especially for the probability or in machine learning application, you may utilize this kind of codes. And so just remember that the demonstration of your code is important to understand and get the underlying mechanism of what's going on in this code. Okay, so the second plot should be created with what the PLT scatter new observations. Okay, but the prediction is equal to the 1 in 0. Okay, and after that we should also give the what in this case 1 and 1 column values in here, and after that we should give the what the marker is equal to the X, color is equal to the red, and label is equal to the class 1. Okay. And the new observation 2 and 2 also be given in here, like O and like blue and class 2. Okay, and also we should give the what the contour of this class XX Y Y Z X1, colors black and line whites equals to 2, and also this is the X2. Okay, so PLT title F Bayesian Decision Classification with 2D GMM, and also we should give the number of components in here, like this one. Okay, after that we should give these terms. Okay, and also we should give the PLT legend. So decision boundary is also given in here, because you may have this utilization. The prediction cannot be defined in here. I'm sorry. S. Okay. Also we need to build the decision boundaries using these terms in the tree line. We should give the PLT, and this is the same code with the previous one. Okay, but we should give this decision boundaries by using the contours. PLT title F decision boundaries. The num components must be given in here, like this one, and PLT X label is height white. What bit basic difference? We should also build the one contour in here, XX YY and Z X1 minus Z X2. Okay, this is the boundary condition of our applications. Levels 0 and colors black and line whites is equal to. Okay, and after the process is done, title should be called and PLT must be shown. So if I run this code, we have the error line 73. I'm sorry, this is the colors. Okay, and this is the colors. $89. I'm sorry, it's not the colors. In the scatter diagram we don't have the colors, but the plot contour must contain these terms. And also, and this is the our final utilizations. Okay, so in the first place we have the graph in here like this one with the two components, which means that if we have 2D data and then one component is showing in here and another component in here, and the Bayesian decision classification with new observation, this data are different from each other, but we can probably create this line or these distributions by using what assign the class 1 and class 2. And after that, if we are using this Bayesian decision classification, and then we have some kind of or this kind of decision boundaries in here, and which means that if the right hand side of these boundaries assigns to the class 2, the left hand side is assigned to the class 1. Okay, but in the second place we have the more stable data or more stable line, because we have used the many components in here like this one. We have 6 components, and so for the one model, for example this model, we have the 6 mean values and 6 covariance values, and then we can reach the smallest change, or we can get the smallest change in the boundary conditions or the data representation by using these terms. And after that, this boundary line is more stable than the previous one. Okay, but if I choose with the addition of for example 10 components in here like this one, okay, we have 3 data in here. But in this case, just remember that in this case we have 2, 6, but in the 10 we have some specific regions in the Gaussian mixture model. We can model it because we have the 10 mean and 10 covariance matrices. And in this case, just simple is that we have the blue line in here, and this blue line is also modeled, even if at the right hand side of these decision boundaries. And we have another boundaries in here like this one, and so we can get it. This good or not, we don't know yet, but we can model by using the increasing the component numbers of these things. Maybe in real-time application this is the error case, or the error is fault in that case. But if we have, or if we want to model everything by using these terms, and so we can utilize this nomination with the high component number. Okay, so that's all for this classification algorithms, and then we will continue with the Navy Bayer classifier.